Well, hello, Christchurch. It's good to see you here tonight. I want to talk to you about poo eventually, but first what I want to do is to get to know you a little bit better. And I'm not looking for samples on this occasion, okay. But I think it's important as a speaker to have some sense of what your audience is about, what they're after, why they're here, to gain some empathy. You know, like those rules of engagement. Notice I don't have any rules. They only apply to you, right? So I can, I feel in some ways there's some asymmetry here, so I'd like to get to know you a little bit better. So I have some questions, a little short survey. I hope you'll participate. The first question I have for you is, how many of you are not from here? Okay, that's quite a few hands. Sometimes, as my students will say, my questions lack precision. So I'm gonna ask this again. How many of you are not from here, the planet Earth? Oh. All right, so I'm not seeing very many hands. Does anybody here have family members distant that are not from Earth? So I feel like already I know you a lot better. I feel like we're almost family. And it's important to have that sense of demographics, because I'm going to talk about extinction, and extinction of the human race in particular. So, and it's part of this conversation about whether we should leave Earth, whether we should go to another planet in order to be more secure as a species. And the inspiration for this talk came from the author Andy Weir, who said, you know, so long as we're an entire species on one planet, we have a chance of going extinct. It could be an asteroid, a virus, a war, or something we haven't even imagined. But right now, humanity has all her eggs in one basket. You are the eggs, by the way, and Earth is the basket. Once we colonize another world, our odds of extinction drop to effectively zero. How many of you find that a compelling statement? Comforting statement? I'm getting a few nods. You're not as willing to tell me that you're not an immigrant, but okay. Some people do, and it's an argument that many governments find compelling. I think I read something along the lines of, averaged over the last 50 years, the world has spent about $1 billion a year trying to get to Mars. So with missions focused on Mars. So it is something that does drive us, this idea to go to Mars. And in particular, it's a dread of an existential threat like extinction. But I want to talk about what it means to be a source of risk of extinction, and to talk about whether or not we can mitigate that risk, whether we prioritized our risks, and whether we can control those risks. All right. We have the Earth is pretty familiar with extinctions. You may be aware that we've already recorded at least 5 mass extinction events since life first appeared on planet Earth. And many think we're in our 6th mass extinction now, largely driven by human activity itself. Now, these mass extinction events look very, very scary. I mean, 85, 95% of species disappearing in one of these events. But I would point out that when we talk about mass extinctions over this period of time, which is about 440 million years, we're talking about big, clumsy species like plants and animals. Things that really are only tourists on this planet, only evolved recently, and probably, deserve to go extinct. The mass extinction really is an extinction of mass, biomass. But as we measure biodiversity, it's not a hugely significant amount of genetic or biological diversity in these mass extinctions. So if you take some comfort in that, that really not that much has ever died, I guess the other way to look at it is that among the things that have died, they're mostly things like you. So the risk is sort of concentrated on you, and that might be somewhat disturbing. So if you're feeling some anxiety, this is the time just to sit back, take a deep breath. Can everyone do that for me, please? Just take a nice deep breath. Now, my next question. What can you not do on Mars? You can't breathe on Mars. Oxygen, we've become addicted to oxygen. And we have a very complex relationship with this little compound. But the Earth itself has also become addicted to oxygen. So it is the heart of what are truly pre-existing, that is, older extinction events, which I would define as truly mass extinctions. The first and probably biggest mass extinction ever on planet Earth was about 2.4 billion years ago. And it's called the Great Oxidation Event. You can see here that the early Earth atmosphere, and when I mean early Earth atmosphere, 50% of the time that Earth has been here, and 2/3 of the time that life was on Earth, we had a reducing atmosphere, almost no oxygen in it at all. But we had tons and tons and tons of organisms. We just don't know how diverse or how many, because microorganisms, which they were, don't preserve well in the fossil record. But about 2.4 billion years ago, some real smart-ass microbes invented photosynthesis. And through photosynthesis, they created oxygen. So rapidly, oxygen began to accumulate in the environment, in the atmosphere. And since all the rest of life didn't use oxygen, it was toxic. Oxygen is a highly reactive atom. So it causes reactions that kill most everything. But it's the original toxin. It's why we spell toxic with the oxygen inside of it. Okay? It is terribly toxic, and it's toxic to you. You happen to have in your cells mitochondria, which are formerly free-living bacteria, who learned not only how to detoxify oxygen, they could also then couple it with energy production, which led to multicellular life, such as you and I. Okay. But my point here is this. This little guy, the microbe, already has dealt with a truly existential crisis, one of its own making, which was the production of oxygen. But then what happened? Well, it made a bunch of oxygen, became addicted to it, and then for some reason started to make less. The second most significant mass extinction event on Earth followed quickly after the Great Oxidation Event, when again another 90+% of the real biomass on Earth disappeared because the oxygen levels went down. We became, since the Great Oxidation Event, inseparable from our need for oxygen. Oxygen is so important, but we even can't make enough of it. Remember COVID? You've heard of this, right? It was a pandemic. We had oxygen shortages. And yet, we're talking about going to a planet that has no oxygen. It's a perpetual pandemic planet. So the amount of oxygen in Mars is trace levels in the atmosphere. You're enjoying 21% in your normal daily life here on Earth. There is no normal environment on Earth that is anywhere near as hostile as every single environment on Mars. So what is this extinction risk? All right. So you remember Andy was talking about asteroids, and we have a fixation with asteroids. By the way, I know everybody has a story about some weird uncle who was killed by an asteroid. Okay? But I'm not trying to belittle risk. But as an extinction risk, it's pretty small. So the odds of an extinction event from an asteroid are 0.501% that we will lose ourselves to an asteroid. Yet we should go to Mars, because now the extinction risk goes to almost zero. Climate change, a disaster of our own making, significantly more important, but still, I'm going to say, not likely to kill you, at least the present audience, because that risk is only 0.05% over the accumulated next 80 years. Meanwhile, we've created extinction risks through our own behavior that almost nobody ever talks about, but are extremely real and could very well kill you, even before you leave the theater. No. I mean, some of you look a little sleepy, but I doubt that that's the sign. Okay. So for example, the odds of dying today because of an infection by a microorganism who is resistant to antibiotics is 0.1%. It's twice the odds over the next 80 years of dying from a climate change related event. The doomsday that we're imagining is around the corner. So I don't want you to be complacent. It's just not the corner you've been looking at. And I think it's easy to frame this, or useful to frame this, from the view of planetary boundaries. So this little graphic here on the left are 9 planetary boundaries, ones that are really important for ongoing life to sustain big, clumsy, tourist-type species like ourselves. And you can see, I think it's like 6 of the 9 we exceed, which means that our present business as usual activity on Earth is at such a scale that Earth cannot renew itself in 6 of the 9 essential functions of a planet to support life like us. And amongst the 2 largest of our transgression of these planetary boundaries is the loss of biosphere integrity, biodiversity, and also these novel entities. And novel entities are the chemistries that we've invented, but also the kinds of organisms we've created. And we've created them either through direct interventions using a biotechnology to make a genetically modified organism, or by selection with something like antibiotics. So that's what this graphic here is on the right. Our use of things like biocides, pesticides, and our use of things like antibiotics are driving the development of novel biological entities as well. Our capacity to produce novel entities is enormous. What you see here in this graph on the left is the rate of increase of new chemical compounds that have been invented and commercialized. The rate of increase, even over the short period of just the last couple of decades, well exceeds population growth. We are inventing new chemical compounds that probably never existed in an oxygen atmosphere on Earth, and maybe not even in a reducing atmosphere before that, at a rate faster than we reproduce. And we are producing them so quickly and throwing them out into the environment so rapidly that they're now coming back to us in the rain. So you've heard of PFASs, those forever chemicals? They come out in rainstorms at concentrations that are considered to exceed safe water standards. You can't escape them. The same is true for our pesticides. Our pesticides aren't just used on farms. They're used here in Christchurch in the park, and you might use them at home. We use them at such a scale globally that they come back to us in the rain. We breathe them in. They adhere to small soil particles that get picked up by the wind. Our capacity to produce novel entities is one of the most important ways to kill ourselves. We're also aware that our bacteria are becoming resistant to the antibiotics, and that's an impending crisis in medicine. And we know that our use of antibiotics correlates with the evolution of antibiotic-resistant bacteria that cause disease in us and our closely related animal species friends. But that is a correlation. Certainly, antibiotics can select antibiotic resistance. But that's not the only thing we've been doing in the last 70 years since we started to produce lots of antibiotics. The other thing we've been doing is producing lots and lots of novel other chemicals. And it turns out that many of these chemicals are toxic to bacteria. And bacteria evolve by inventing the most generalized detoxification systems, like oxygen. If it's a global response to a major toxin, you want the simplest way to resist it. So what else correlates with antibiotic resistance is our massive commercialization of novel chemistries. And what we see worldwide is an increase, an incremental but steadily increasing level of resistance to antibiotics. The simple mantra that if we just stop using antibiotics, we'll restore the earth to one in which an infectious disease can be treated again is probably wrong. And it's very close. It's very close to you here in Christchurch. So this is a little sample of our own research. Here on the right is a list of E. coli that we've gotten from the Avon River, which is just right next door to us now. And E. coli, if you don't know, is your poo. So this is where we come full circle in a way. Most of the dry weight of your poo is this organism. And there's a lot of it in the Avon River. And what you see in these boxes, every place there's a box, it's an isolate that's resistant to an antibiotic. And it's very easy to go into the Avon River and isolate E. coli that are resistant to multiple antibiotics. And in fact, we can't go into the Avon River without isolating at least a handful of E. coli that are resistant to every clinically useful antibiotic. That means if you're infected by an E. coli from the Avon River, either a gastrointestinal infection or a skin infection, it could be completely untreatable. The treatment is decapitation or asphyxiation, but it's probably not walking out of the hospital.
Okay.
And we're affecting other planetary boundaries at the same time. So bacteria become resistant to these antibiotics, in part by sharing the resistance genes among themselves. It's called horizontal gene transfer. And this little graph on the left is showing you that animals, not just you and I, but also mussels and cockles, the kinds of things we like to pull out of the river and eat, we concentrate those bacteria and accelerate the rate of gene exchange between them. So in this little experiment, my PhD student, Sophie, showed that horizontal gene transfer can occur 1,000 times more frequently in the belly of a mussel, which you eat, than in the water itself. So we're little incubators that are producing antibiotic resistance in the pathogens that cause us infections. So this kind of reminds me of a story. And you probably know the story. It's that scorpion and the frog, and does anybody not know that story?
Tell us again.
Yeah, I'm going to because some people were too shy to raise their hands. So the scorpion and a frog, they're waiting next to this river. For some reason, they want to cross it. I think it's something like with a chicken and a road. But in any case, they're motivated. They're motivated to get across this river. And the frog has a way. It's called swimming. The scorpion doesn't have kind of equivalent. So it says to the frog, listen, you know, I don't weigh much. Just take me. But the frog, you know, the frog is smart and says, no, you're a scorpion, and you're going to sting me, and it's not going to be pleasant for me. And the scorpion says, look, you know, obviously we're in this together. I'm not going to sting you, so let's just go across the river. So the frog, not as smart as I originally advertised, takes on the scorpion, and halfway across the river, the scorpion stings the frog to death, and they both drown. But just before the frog dies, it says, why'd you do this? You know, it defies the logic you set up before in the contract. And the scorpion said, it's my nature. And this is, when I look at extinction risk, when I look at the probability and sources of extinction risk, and I think, well, would going to Mars help me ameliorate that risk? Would it create a safe passage or a safer passage for humanity? And I wonder why we think of Mars and at the same time are turning Earth into Mars. A trip to Mars might save us from a vanishingly small, almost negligible risk of death by asteroid. But it won't save us from extinction because we are the major cause of our own extinction. Thanks. Some of you are smiling.
Six for I.
Any questions? Yeah. You mentioned PFAS earlier.
I mentioned PFAS, yeah. Mm-hmm.
Yeah, how does it end up in our brain? I don't quite understand that.
Multiple ways. So first off, we send a lot right into the atmosphere, like through fire retardants, you know, those big fires in the US. Yeah. So some of it is directly introduced into the air. But these chemicals also bind to small particles, soil particles, microplastics, all sorts of other things, and then they can be picked up in the wind. They get into the atmosphere, and when it condenses and the water comes through, it just pulls those particles down. But they're in packages that are really well designed to get into our lungs. They're good size for that. Yes, please.
Knowing that Mars isn't going to be or shouldn't be the life raft we are talking about, but we have billionaires, and billionaires have egos, so we're going to end up there anyway. Is there anything we can do to mitigate some of these problems about that you've discussed, given the clean slate that we'll have with Mars?
Right. So could we design Mars in a way to avoid some of the problems here? And I guess my answer still is a little cynical, because we've been designing Earth. It's not like we just happened here, right? We have been using our techno-utopian visions to create an Earth that we think is wonderful, and in the meantime have exceeded planetary boundaries for sustainability. So when we look to a technology to be our salvation, within that are the roots of our own demise. Until we've learned the lessons about how to live sustainably, including any use of responsible technology, should we really, expose another planet to us? We may have to think that it won't be a solution for us if we take those same ideas along. And as you mentioned, it's the billionaires disproportionately responsible for the way the Earth looks. And they're techno-utopian dreamers. They're using and are fascinated by a technology that's sophisticated enough to get us through the vacuum of space and land on this planet. Meanwhile, all the astronauts have poo full of antibiotic-resistant bacteria in close quarters. Not to say it's impossible. There was the lights are hard, but I think there was someone back here first, yes.
Yeah, it was a similar question really to the previous. I mean, apart from not skinny dipping in the Avon, what can we do, or is the conclusion we're stuffed?
It depends on how attractive you are when you're naked, because even E. coli, has taste, right? It's not a taste that we often enjoy. But it's not your only way to be exposed. I guess the point is that if it's in those concentrations in the Avon River, then it's at really high concentrations everywhere in your environment. The Avon is just a sentinel for what's flowed into the Avon, right? And those E. coli are also, like the PFAS, attached to small particles. They're in the wind. A study that was done in the US looked at antibiotic resistance genes in the air. And they looked both upwind and downwind of what are called concentrated animal feeding operations, CAFOs. In the US, there's massive cattle CAFOs, swine, chickens. In New Zealand, we have CAFOs too, but mainly chicken CAFOs, maybe a few other species, but you know, we have them too, so it's not just the US. This study found that there were 10,000 times the number of antibiotic resistance genes downwind of a CAFO as upwind. So the poo of these animals dries out, gets picked up, and circulated. And that's, you can't avoid it in the same way that you can avoid the Avon River. I don't know if you've ever been on a weekend in Hagley and you see people throwing sticks into the Avon and their dogs are going to get it, and then the dog comes out and shakes all over them, licks itself and licks them. Your cat runs around the neighborhood through pesticide lawns and then comes in and poos, creates an aerosol. So there's so many ways in which you're being exposed. And the Avon is telling us that there's lots of exposure pathways that have nothing to do with the Avon. Yep.
I was just saying, thanks, Jack. Good talk, but I'm disappointing related to poo. So come back again.
Remember the rules of engagement? Would you consider that a heckle?
Sorry. So my question was about antibiotics, and I'm just trying to formulate the exact question as I talk. If you could go back in time to pre-antibiotics and talk to, you know, the developers and inventors of the early antibiotics, would you stop antibiotics being developed because they have saved a huge number of lives?
They're the foundation of our modern medicine, right? Yeah. There's all sorts of things we use antibiotics for that have nothing to do with treating an infectious disease. They're prophylactic before you have a surgery so you don't get an infectious disease. And they're the foundation of our highly intensive animal feeding operations. So a lot of Earth's calories for meat production are based on antibiotics still working. But I don't have to give you a hypothetical of what would happen 70 years ago at the beginning of the commercialization of these kinds of antibiotics. Because people like me were telling the industry and government that if they used antibiotics in the wrong way, the outcome would be massive resistance to antibiotics. And the response was, it's okay. We'll just put in private incentives to invent new antibiotics. And that worked until about the 1970s. And now the commercial model doesn't work. And in fact, there's real theoretical reasons to believe that we will never have a future antibiotic discovery era that comes anywhere close to what happened between the 40s and the 70s. That we have exhausted the real thick, rich veins of antimicrobial compounds for that purpose. Because remember, they're very special. They're ones that kill bacteria before they kill you. Antibiotics are not nice to you either. Penicillin was perhaps the most magical of them and had the least toxicity, though there are still allergic responses. But most antibiotics are not nice to you. And what limits how much you can take is their toxicity to you. Right? So all the bacteria have to do is be resistant to the level that still kills you before we'll stop using it. Okay? And one of the reasons for that is because you have mitochondria. Remember those mitochondria? The things that are protecting you from oxygen? They're bacteria. So our cells fused with these bacteria a billion years ago. And the antibiotics kill your mitochondria, right? So then you go back to your original toxin. Could we have used antibiotics in a different way and had a different outcome? I think the answer is quite possibly yes. But can we back up to that? The answer is quite likely no. Because once we've exhausted that non-renewable resource, once resistance has evolved in the species that cause us disease, it doesn't de-evolve. It doesn't go away. It goes down in frequency, but as soon as you reintroduce the antibiotics, those bacteria come right back. Right? So every time we invent a new antibiotic, we steal a future generation, we steal from a future generation the ability to use that antibiotic for medical purposes. Or we steal it from a future new planet. Because once we take an organism that is resistant to that planet, you can't get rid of it. Yeah.
Thank you.